So let's consider another situation. Let's consider a loop of wire. Okay, so top view of the loop is like that, side view is like that, and I want to know what's the magnetic field at the center of that loop. Okay, so we're going to assume the loop of wire has radius r. Okay, and I want to know the magnetic field at the center. I'm going to assume the current is going this way. Okay, so right-hand rule tells me that if I put my thumb in the direction of the current, that whatever I put my fingers around here, that's going to be coming out of the board in here. So that means it's coming out from the center. Another way of thinking about this is that for a coil of wire, if you curl your fingers in the direction the current's going around the coil, your thumb points at the direction the magnetic field is going in the middle of the coil. So now I want to figure out what's the strength of that magnetic field in the center of that loop of wire. Okay, so we got this loop of wire, and I want to find out the magnetic field in the center of the loop. Okay, so law of Biot-Savart says that dB is going to be equal to mu naught over 4 pi I ds cross r hat over r squared. Okay, so let's look at that. For our loop right here, the ds is going to be that distance right there. Okay, well, that distance right there is going to be equal to r d theta. Okay, we talked about this sort of thing in physics 1. So we're going around a circle here. The arc of a circle here is going to be equal to r theta. And so it's going to be equal to, the ds is going to be equal to r d theta. Okay, and so that means that, and then the cross product, because we're always perpendicular to the radius, then the cross product just gives us 1. So that means the dB is going to be mu naught I over 4 pi times r d theta over r squared. Well, that r cancels that r. Okay, so dB mu naught I over 4 pi r d theta. Okay. Well, all we got to do to find b is integral dB. So that's the integral of that mu naught I over 4 pi r d theta. Well, notice everything comes out of the integral except d theta, because I'm integrating around theta, so none of that depends on theta because it's a circle, so r is constant right here. So r is going to be constant. So I integrate from 0 to 2 pi d theta. Now, why did I not integrate 0 to 360 degrees? Because for an arc, that arc length is r theta if theta is measured in radians. So you have to measure in radians. So I have to integrate 0 to 2 pi. Well, it's going to be b mu naught I over 4 pi r of theta evaluated at 0 and 2 pi. Well, that's 2 pi minus 0. So that means that this is going to be mu naught I over 2r. So that is going to be the magnetic field in the center of that coil of wire. Next thing we're going to do is imagine we have a coil wire and we're some distance z above, and I want to know the magnetic field. Okay, that actually turns out to be a substantially more complicated situation right there. Okay, so that's considerably more complicated than finding the magnetic field otherwise, because now at that point you've got a situation in which the magnetic field is going to be at angles there. And so that's substantially more complicated. Okay. And so because of that, that's going to be a little, that'll be something that normally you would see in an upper level class. Okay. So we could probably do that, but it would be a little bit more work than we really need to do for this level class. So you get a break on that. Okay. So just thought you might find that interesting to know that you actually can extend this topic to something that's considerably more complicated.